Hey guys, good morning, good evening, good afternoon. I'm bringing you another video which is a sequel to a series of videos on microgrids. So I've done two videos before. One talked about an introduction to what microgrids are, and the other was about what research areas are prevalent on microgrids these days. So again, introducing myself a little bit. My name is Khurram Hashemi. I am an electrical engineer and I did my bachelor's, master's and PhD in electrical engineering. So during my PhD, I worked on the control of microgrids and how to devise new control methods in a hierarchical control paradigm. All right. So currently I'm teaching at the University of Engineering and Technology, Lahore, abbreviated as UET, and this is in Pakistan. And before this, I have worked at the University of the Shanghai Jiaotong University, abbreviated as SJTU, in China, as a research assistant where I was doing my PhD. So anyway, let's get back to our main area of talking, what we want to talk about today. So microgrids, basically, to introduce and to summarize again, is an independent power network that works independently of the power system and has a host of resources such as PV modules and micro turbines that might include gas turbines and diesel generators, and then you might have a energy storages. So you might have battery energy storage systems, or you might have a fuel cell, and you might also have something like a wind turbine or a wind farm. So it depends on the size of the microgrid. And then obviously you have domestic loads and industrial loads. So you have storages, you have sources, and you have loads. And to manage this, you have controls at the local levels as well as on a semi-central level. And then if you want to coordinate more than one microgrid, so if this is another microgrid and this is one microgrid and this is another microgrid connected to the same network, then you might also have a distributed network operator that coordinates the interaction of these microgrids together and the interaction of these microgrids with the greater power system. So in my previous video, I highlighted a couple of ideas that are being worked on these days. So one of those was the semi-hierarchical control of microgrids. So to recap a little bit, so this time I'm going to draw like this horizontally. So we have a couple of buses that are connected with transmission distribution lines, and each one has its own reactance and resistance. So this might be the similar or might be a little bit different, and then we have this connection to the external world through a transformer. This is basically a transformer. You can say YY transformer or Y delta transformer, and then this is the power system. So now the people working on power system studies will be very familiar with these diagrams. So now each and every one is going to have an LC filter or LCL filter. So some might have LC filters, some might have LCL filters, but in a domestic residential colony or something, you might have similar setups, because every home will have a home integrated PV system, right? And here we have I'm going to skip the PWM control part, because it's understood that most techniques use PWM. So we have a DC to AC converter. So that's called an inverter, usually a DC to AC converter. And then to control this, we have different control loops. So we have a voltage control loop. Sorry, let me write in order. We have a current control loop, and then we have a voltage control loop. And likewise, we have the same here. So I'm gonna represent with symbols now to make it quicker, so I can catch up while I talk, because I talk faster than I write. So now above this we have the power control loop that comes up with local references of active and reactive power. So P means active power and Q means reactive power. Those who are unfamiliar, you can read up a book called Power System Analysis by Duncan and Glover. Let me write this here. Power System Analysis by Duncan and Glover. So this is a book that's used to teach bachelor's level power system analysis. So if you don't know these concepts, you can just come back here and read this. Okay, it's not moving, so I'm gonna just leave it there. And then these are also gonna have the same PQ loops. And then above this, you will have, because the control here works by changing the angle and the voltage magnitude. So these two parameters are going to change for every one. So if this is the first inverter, this is going to be different from this, and this might be different from this. So this angle, power angle, translates into the frequency, right? And we have to maintain the frequency within a very short range. So if it's 50 hertz, we might not be able to go beyond 0.1 hertz, or if I talk more liberally, 1 hertz at most, and the system might just go into oscillations. So we have to keep it in a very short range. So here is the one I follow. So we have to have restorative loops for voltage and current, voltage and frequency, right? So you can say restorative. Do not confuse with some other thing. So the subscript R means restorative. So what this does is that it keeps interacting with the frequency here and the voltage here. So it keeps sending back these values to ensure that these are within range, right? So I'm going to stay until this level here, and this is the kind of hierarchical control that we did even in my PhD, and this is a very popular control scheme these days. So what happens is that I'm going to highlight some things for you. So what happens is that this is the localized control. So it's a pretty mature area. That deals with the inverter control, and the methods are well established, and there is a PWM here, or state vector modulation, or some other method. And then we have a power control here, that most popularly uses the droop method. I'm going to talk about it a little bit later. And then we have a restorative control here. So these two controls, at least this control is localized. So this control may be cooperative, and this control is usually cooperative. So what cooperative means is that it talks to its neighbors and then receives information from its neighbors, and talks to its neighbors, receives information from its neighbors, and this is how this control ascertains the fact that the frequency and voltage are within limits. All right. So let's come back here. So power control, the basic philosophy for this is that if you have a bus here and there is a source attached here, so the angle at which, so if this is the system frequency attached to the power system here, and if this is the system waveform, then the difference of this waveform with the waveform your inverter is producing, this one, is going to give you the, let's represent it by this, is going to give you how much power is flowing from here to here, right? So the angle difference is proportional to the active power. And the magnitude of the voltage, so the magnitude of the voltage is proportional to the reactive power. So the greater the voltage, the greater the reactive power, and then you can say the greater the angle difference, the greater the active power. So if you integrate this angle, it turns out to be the frequency, or rather the angular frequency. So you can predict where the frequency is going. So let me draw you this diagram. If this is the active power being injected from here to here, and this is the angular frequency, so when there is a demand for greater power, we have this kind of a characteristic, and for a higher frequency, less power is drawn, and for a lower frequency, greater power is drawn. So if this is omega 1 and this is omega 2, so then omega 2 is going to be less than omega 1, whereas the corresponding power to omega 2, P2, is going to be greater than P1. So this is called the droop characteristic. And this comes from the traditional knowledge, because the generator is connected to a turbine and it rotates, and then this creates a three-phase voltage and current, right? So when there is a greater load here, an electrical load, this translates into a mechanical load on this side. And then the turbine experiences a greater torque, so it has a sort of a droop characteristic. Even this has to be controlled, otherwise it might not be straight. So the generator control makes it a straight droop characteristic. So this has been borrowed from the traditional power system mechanisms and programmed into modern power electronics, so it can easily connect with other mechanical generators in the power system. So it should be able to synchronize like this with other generators connected in the system. So that was the basic idea. But these days we're having some more ideas. This one is the basic idea that has been in use for a while. So what this does basically is that it reduces the frequency at the inverter terminals, and overall the frequency of different inverters might be different using this control method. So we need a overall restorative system to restore the frequency. So that's where this level comes into play. So what this does is, let me call it a cooperative control. And I'm going to just go into the basics here, and I'm going to talk about the details in another video. So let's say that we have several inverters. So I'm just going to draw a symbolic diagram and not go into all the specifics. So this is the transmission, this is the distribution line, and this is the bus 1, bus 2, bus 3. And here's a couple of inverters here. Okay. So let's represent each inverter by a circle. So you can call this a node in the network. So this is node 1, this is node 2, this is node 3, this is node 4. Now the goal is to make these nodes talk to one another so that they can share information. In this case, information of what the voltage is and what the frequency is. So it's two pieces of information. So this set has two values. So this one is going to put this value into the network, and then this value is going to get carried forward with this information here, and this information V1, F1, V2, F2, and so on. So the information set is going to grow as it travels. Now this creates a problem that we have a large packet rotating in the system. So how to make this more viable? So what we do is that every node processes the system in a way, these values in a way that takes an average of the value, and that average rotates in the system. And that's what's used to find an error. So the local value minus the average gives the error. Let's call this X error, right? Now this is the corrective term. Now what we do is that we make one node the leader. So this node gets the reference, the true reference, the global reference, and then the effect of this reference slowly travels through the system using this communication network. So mostly this is an Ethernet or some other communication media, and then overall the system voltage improves like this. So if usually the system voltage is a little bit like this. Some inverters are higher, some inverters are lower, and then at some point all of them will converge. So if this is the time and this is the voltage magnitude, at some point they will all converge. Same goes for system frequency. So if this is time and this is, say, converted frequency in hertz, then different inverters are going to have different frequencies, and then at some point by the effect of the control network, this one, cooperative control, they're going to converge. So usually this is 3 to 4 seconds, maybe less. And same goes for this, 4 to 5 seconds and maybe less. So this is called a distributed cooperative control. Has been very popular since 2013, and many papers have been published. Especially, I'm gonna write some famous names. So there is Professor Josep M. Guerrero. I hope I'm writing his name spelling correctly, because he might be watching this video. And then there is Blaabjerg, also from the same University of Aalborg. And then there is, especially this work has been done by Professor Frank Lewis and his group of students, which includes, I hope I'm right when I say Ali Dawoodi and others. So a lot of famous names here. I don't remember all of them, but I hope they'll forgive me, because I've read all of these papers. And then many other people have also adopted the techniques, including myself. So it's a lot of good work has been done. Then some people have tried to combine these two together, and make it into one control. So they've tried to combine the power control with the voltage and frequency restorative control. So this was mostly the more important factor in this control was reactive power, because it could not properly be achieved with the Droop method. So the Droop method for reactive power is a little bit like this. So the increase in reactive power is, so the greater the magnitude of the voltage, greater the magnitude of the voltage, the more the reactive power injected into the system, right? It's like this. But it doesn't work that well usually, because the inductive nature of the microgrid or the resistive nature of the microgrid comes into play. So some people invented a method where they would combine the distributed cooperative control with the control for reactive power, and this work has been done by Johannes Schiffer. So I've spoken to him a few times. Very good work, and if you search by the name J. Schiffer, you'll find his papers. I'm not sure if his name has an edge or not, but you can check both. So IEEE, transactions, and others. All right. And then some people, such as myself, have worked on that if there is some delay in these communication links or complete breakage, then how we could make this control resilient to these kinds of faults. So we included some advanced averaging and prediction methods, but we tried to keep it simple, so we did some work on this. So this is the kind of things that have been happening, particularly in hierarchical control of the microgrid. And then some people say that until this point we can have a decentralized control or a cooperative control, and this control may be centralized or partially centralized. So that is another method that was popular before, and some people still argue that some people still say that this method should be used. So that is the way research goes. Many people have different ideas and they present it, they experiment with it. So in some cases some methods are more successful, and in other cases other methods are more successful. Okay guys, I think this video has become pretty long, so I'm gonna conclude it here. If you have any questions, you can email me at Khurram Hashemi at uit.edu.pk, or you can contact me on LinkedIn, or you can add comments to this video. Please do subscribe to my channel and press the bell icon, so whenever I upload a video, you can know it. All right, happy face. See you soon. Bye bye. Have a good time.